Today I have an interesting question for you. What features of the original graph cause the simplex graph to not contain a Hamiltonian cycle or Eulerian circuit? Before we tackle this question, let's do a quick recap. The simplex graph of a graph G is a graph where the vertices correspond to cliques in G, and in which two vertices are adjacent when their corresponding cliques in G differ by the presence or absence of a single vertex. Note that adjacent vertices correspond to cliques whose sizes differ by 1, meaning that adjacent vertices correspond to cliques of different parity. This implies that simplex graphs are bipartite, because vertices corresponding to cliques of even size only link to vertices corresponding to cliques of odd size, and vice versa. Alright, now let's get to our question. Are there any characteristics of the original graph that always lead to a simplex graph that is not Hamiltonian or not Eulerian? We could start by asking about criteria for Hamiltonian cycles in bipartite graphs, as simplex graphs are bipartite. For any bipartite graph, if there is an odd number of vertices, there does not exist a Hamiltonian cycle. This comes from the fact that bipartite graphs do not have odd cycles. What does this say about Hamiltonian cycles in simplex graphs? Well, the number of vertices in a simplex graph is the number of cliques in the original graph. So this tells us that if the original graph G has an odd number of cliques, then the simplex graph K of G does not contain a Hamiltonian cycle. Another way we could analyze the existence of Hamiltonian cycles in a simplex graph is to think about some structures that guarantee the non-existence of a Hamiltonian cycle. Graphs with a vertex of degree 1, for example, cannot contain a Hamiltonian cycle, because once we visit that vertex of degree 1, there's no way to get back to it. Applying this to simplex graphs, if we had even a single vertex of degree 1 in our simplex graph, that simplex graph could not contain a Hamiltonian cycle. So this leads us to the question, what do vertices of degree 1 in the simplex graph correspond to in the original graph? For starters, they correspond to cliques of size at most 1, because vertices corresponding to a clique of size n have at least n downward neighbors in the simplex graph. That is, neighbors formed by excluding a single vertex from our clique of size n. For example, the vertex corresponding to clique ABC in this graph G will have downward neighbors AB, BC, and AC in the simplex graph. Also, if a graph has at least two vertices, the vertex in the simplex graph that corresponds to the empty clique will have at least two neighbors. Together, this tells us that for graphs with at least two vertices, vertices of degree 1 in the simplex graph correspond to cliques of size 1, that is, vertices in the original graph. The degree of a simplex graph vertex corresponding to the one clique V in the original graph is one more than the degree of vertex V in the original graph. So if a vertex V in the original graph has degree at least 1, the vertex corresponding to one clique V will have degree at least 2. Finally, this lets us say that the vertices of degree 1 in the simplex graph correspond to isolated vertices in the original graph, provided that graph has at least two vertices. As an example, this graph has a vertex that is isolated, vertex C, and the simplex graph vertex corresponding to the one clique C has degree 1. The simplex graph is not Hamiltonian. So we now have two tests that we can apply to a graph to find out whether its simplex graph is not Hamiltonian. If a graph has an odd number of cliques, its simplex graph is not Hamiltonian, and if a graph has any isolated vertices, its simplex graph is not Hamiltonian. You might notice that our second test also helps us find out whether a simplex graph is not Eulerian, as vertices of degree 1 in any graph do not allow for Eulerian circuits in addition to not allowing for Hamiltonian cycles. Next, let's look at how vertices of degree 1 in the original graph affect whether the simplex graph is Hamiltonian. As you can see, the simplex of G shown here has a Hamiltonian cycle, and G has vertices of degree 1. So the mere presence of vertices of degree 1 is not enough to rule out Hamiltonian cycles in the simplex graph. However, notice that vertices of degree 1 in the original graph essentially become vertices of degree 2 in the simplex graph, with one downward and one upward neighbor. Next, notice that in the list representation of the Hamiltonian cycle of any simplex graph whose original graph contained vertices of degree 1, the simplex graph vertex, corresponding to a vertex V of degree 1 in the original graph, must be listed in an adjacent position to the simplex graph vertex corresponding to the empty clique. In other words, the edge that links V to the empty clique in the simplex graph must be traversed in any Hamiltonian cycle of the simplex graph. An easy way to see this is to start our cycle at the empty clique vertex, and suppose for contradiction that we can complete a Hamiltonian cycle without crossing the edge that leads from V to the empty clique vertex. At some point, we must visit V, which will have to be through the only other edge it is incident to. Yet, at that point, we have still not returned to our starting vertex, meaning that to complete the cycle, we must pass through our forbidden edge. We can almost formulate our observations into a test for the presence of Hamiltonian cycles in a simplex graph. To help us do that, let's make another observation. Look at what happens if we have more than 2 vertices of degree 1. Suppose we had 3 vertices of degree 1, x, y, and z, which turn into vertices the 1 clique x, 1 clique y, and 1 clique z in the simplex graph. We would have to use all of these edges in our Hamiltonian cycle, which would imply that we would be visiting the empty clique vertex more than once, something that is impossible in a Hamiltonian cycle. This gives us a new test. If a graph has more than 2 vertices of degree 1, its simplex graph is not Hamiltonian. As our last test, consider a disconnected graph composed of n greater than or equal to 2 connected components. The result of taking the simplex graph will always be a connected graph. So at first you might think maybe it could be Hamiltonian. However, the simplex graph of a disconnected graph like G will have the following structure. The simplex graphs of each component will be subgraphs, and the vertices in each subgraph that correspond to cliques of size 1 in G will be adjacent to the empty clique vertex in our simplex graph. There can be no adjacencies between vertices that correspond to cliques in different components in the original graph. The only adjacencies are between vertices representing cliques in the same component. Since the empty clique is the only clique present in all components, it is the only vertex in the simplex graph allowed to have adjacencies to cliques in different components. Now suppose for contradiction that we do have a Hamiltonian cycle in this simplex graph. Let's start our Hamiltonian cycle at the empty clique vertex. Intuitively, no matter which subgraph we choose the next vertex in our cycle to be from, we'll never be able to reach any of the vertices in any other subgraph without visiting the empty clique vertex again, so we would be stuck in that subgraph. So any simplex graph whose original graph is disconnected will not contain a Hamiltonian cycle. As an example, see the simplex graph of this disconnected graph with 3 connected components, and observe how it's not Hamiltonian. Let's list all the tests that we found so far. If a graph has an odd number of cliques, its simplex graph is not Hamiltonian. If a graph has an isolated vertex, its simplex graph is not Hamiltonian nor Eulerian. If a graph has more than 2 vertices of degree 1, its simplex graph is not Hamiltonian. And if a graph is disconnected, its simplex graph is not Hamiltonian. And if you notice, the fourth test is just a generalization of the second test. To demonstrate these tests, here are a couple more examples of graphs that are not Hamiltonian. Without finding the simplex of this graph, can we say whether it's Hamiltonian? Well, let's list out the cliques, and if you count them up, there's 11 of them, which is an odd number. So by our first test, the simplex of this graph is not Hamiltonian. Next, what about this graph and its simplex graph? There are a lot of cliques here, so maybe we don't want to list them all out. Thankfully, we can see it has an isolated vertex, so the simplex graph is not Hamiltonian by our second or fourth tests. Finally, how about this graph? We have 3 vertices of degree 1 here. So by the third test, the simplex graph will not be Hamiltonian. Moving on, let's look at a few tests for Eulerian circuits in a simplex graph. It's known that a graph has an Eulerian circuit if and only if all its vertices have even degree. If we look back to one of our previous results, it must be that if a graph has even a single vertex of even degree, its simplex graph has at least one vertex of odd degree, meaning it's not Eulerian. So a necessary condition for a simplex graph to have an Eulerian circuit is that all the vertices of the original graph have to be of odd degree. Additionally, the empty clique vertex in the simplex graph will have degree equal to the number of vertices in the original graph. This means that if the original graph has an odd number of vertices, then the empty clique vertex will have an odd degree, and our simplex graph will not be Eulerian. As our final test, let's think about the simplex graph vertices corresponding to maximal cliques. If a simplex graph vertex V corresponds to a maximal clique of size n in the original graph, V has degree n. This is because it only has downward neighbors. So, if the original graph has any maximal clique of odd size, then the simplex graph has a vertex of odd degree and is not Eulerian. As an example, see one of the first simplex graphs we covered in this video, and note how vertex ABC in the simplex graph corresponds to a maximal clique of size 3 in the original graph, and that it has exactly 3 neighbors in the simplex graph. If we list out our tests for Eulerian circuits, we have: if a graph has an odd number of vertices, its simplex graph is not Eulerian. If a graph has vertices of even degree, its simplex graph is not Eulerian. And if a graph has any odd maximal clique, its simplex graph is not Eulerian. Here are some examples of graphs whose simplex graphs are not Eulerian. The leftmost graph has an odd number of vertices as well as a vertex of even degree. So by tests 1 and 2, its simplex graph is not Eulerian. The middle graph has vertices of even degree. So by the second test, its simplex graph is not Eulerian. Finally, the rightmost graph has 2 maximal 3 cliques, as well as vertices of even degree. So by tests 2 and 3, its simplex graph is not Eulerian. Altogether, here are the 7 tests we covered in this video for graphs to be not Eulerian or not Hamiltonian. Moving on, we've spent a lot of time looking at graphs whose simplex graphs are not Eulerian or not Hamiltonian. To finish the video, can we instead construct a family of graphs whose simplex graphs are Eulerian or are Hamiltonian? The path graphs are one family of graphs whose simplex graphs are Hamiltonian, as the simplex graph of a path graph with n vertices contains a cycle graph with 2n vertices as a spanning subgraph. Moving on to Eulerian simplex graphs, the graphs formed by the disjoint union of complete graphs with an even number of vertices is a family of graphs whose simplex graphs are Eulerian. To show this, we only need to show that the degree of each vertex in those simplex graphs is even. First, notice that the set of cliques in the disjoint union of two graphs G and H is the union of the set of cliques in G with the set of cliques in H, and that these sets are disjoint with the single exception of the empty clique, which is in both clique sets. Next, let's define the concept of a neighboring clique, which is a concept we've already touched on a little bit earlier in the video. We can say that two cliques are neighboring if their corresponding vertices are adjacent in the simplex graph. In other words, they are neighbors if one can be formed from the other by the inclusion or exclusion of a single vertex. As discussed earlier, in graphs with more than one connected component, such as a graph formed by the disjoint union of two other graphs, a pair of cliques can only be neighbors if they are in the same component. The number of neighbors of a clique is its corresponding vertex's degree in the simplex graph. Now, observe that in a complete graph with n vertices, each clique will have n neighbors. For example, in k sub 4, each clique will have exactly 4 neighboring cliques. By the inclusion of a single vertex, we can turn AB into ABC or ABD, and by the exclusion of a single vertex, we can turn AB into A or B. This means that the complete graph with n equal to an even number of vertices has an Eulerian simplex graph, as each vertex in the simplex graph will have n neighbors and n is even, meaning they will each have even degree. Putting all these observations together, what happens when we take the disjoint union of complete graphs k sub x and k sub y, each with an even number of vertices? The resulting graph's clique set will be the union of the clique sets of each complete graph, and there will be an even number of vertices in this union graph, meaning our empty clique will have even degree. And all other vertices in our graph, corresponding to cliques of size 1 or greater, will have the same number of neighbors in the disjoint union as they had in the graph they came from, which will be an even number. So every vertex in the simplex graph will have even degree, meaning that the simplex graph is Eulerian. We've just built a family of graphs whose simplex graphs are Eulerian. Here are a few examples. That's it for this video. We could go a lot deeper into analyzing the structure of simplex graphs based on their original graphs, and we could also look at how this affects Eulerian trails and Hamiltonian paths. I highly encourage you to do this on your own. In future videos, we'll investigate more properties of simplex graphs, including whether isomorphic simplex graphs imply that the original graphs were also isomorphic. Thanks for watching. Please subscribe if you enjoyed the video. Have a great day.